So let's do our first problem for our practice exam, and that is potential, potential, potential. So I'm looking at metallic material, chromium. So chromium I know is a BCC material. Looks like this. I know that I have this here. My number of nearest neighbors, or my Z, effectively is going to be 8. My R naught is going to be my equilibrium distance, which is going to be equal to 2R, which I can look up in my handy-dandy table, my periodic table. And if I look up chromium, if I look it up over here, I can see that chromium has a 1.3 angstrom distance, metallic radius. So my R naught is going to be 2.36 angstroms. And we know in our unit cell here, A is equal to 4R over square root of 3, or equal to 2R naught over square root 3. So these might come in handy a little bit later. So we're given this chromium. We're told the energy per atom is 1.2 times 10 to the 20th eV negative. We're given a Young's modulus. So I'm going to use the expression, we already know what our R naught is, and we are asked to find these fitting parameters. So I know that my energy per atom is going to be equal to Z over 2 times U of R evaluated at basically R equals R naught. And my Young's modulus is going to be equal to Z over 2 R naught times second derivative of U with respect to R squared evaluated at R equals R naught. So with this expression, I could start to solve using my Mathematica notebook. So we open up Mathematica, and now we could go ahead and start to kind of solve through this problem. So I've got my potential here. So let me zoom in for the viewers. So I've got my potential. So UR equals epsilon times exponential minus 2 times A minus R. Actually, start 2A. R minus B, and then minus 2 times exponential minus A times R minus B. And let's make sure we close this one here, and then close this one here, and we've got it. Voila. So I know to get my R naught, I'm going to solve set derivative of UR with respect to R, set it equal to 0, solve with R, give me the reals. And R equals B, so our R naught we already said was equal to 2.6 times 10 to the minus 10 angstroms, and B equals R naught. So we have that. So one of our fitting parameters is done, and that is in meters. Now we're told the energy per atom, so E atom is equal to negative 1.2 times 10 to the minus, or 10 to the 20. And then that is in electron volts. I need to multiply by 1.602 times 10 to the minus 19. So that's going to be my energy per atom. And that is going to be equal to solve E atom. Set that equal to, it's Z over 2. So if we look over here, my energy per atom is Z over 2 times Z over R. So that is just going to be 4 times basically UR slash dot. Basically R goes to R naught, and then I want to solve that. So actually we can look at that first. So let's look what this, let's take a peek what this looks like. And then, so I'm going to solve that for epsilon, and then give me the reals. And my epsilon equals 4.0, so epsilon. My epsilon is in joules, so that's my epsilon. Got that. So now I can figure out my Young's modulus. So my Y is equal to what? 140 gigapascals. 40 times 10 to the 9. And I can solve that Y set equal to, again, 0 over 2. So it's basically 4 divided by R naught times derivative of UR with respect to R to the 2. Oops. Slash dot R goes to R naught. And then we're solving for A reals. So I get the positive value because I can't have a positive inverse, and these are all this is an inverse meter, so that's my A. So we solved it. If temperature increases, how would the potential change? So if I have my normal potential, it looks like this. if my temperature increases, it would look like this. My R naught would change and my potential would kind of widen a little bit. So I get like this and like that. Because my Young's modulus for metals, ceramics will decrease as temperature increases for ceramics, amorphous polymers, and metals. That's generally true. If I have a stiffer material, like this orange one, it'd have an even basically sharper curvature because my Young's modulus is proportional to my curvature. There we go. So if it's more compliant, it would look like, again, essentially flatter, less curvature. So what is the theoretical maximum force that this material can withstand? What is the strain the material experiences at this maximum force? So my force is equal to, or my pulling force is equal to, again, generally a force is negative the gradient of potential, but here the pulling force that I could exert when I basically pull on this, so let me go over here, when I pull on this material like this, that force is going to be just the potential, the derivative of UR with respect to R. So that's my force. So if I want to solve where the force is maximized, solve derivative of Ft with respect to R, set this equal to 0, and then solve for R. That should get me the reals as well. So that's my R max. So my R max is equal to that. So that's my R max. So if I want to do my F max equals F sub T slash dot R goes to R max. That would be my force. And then finally, if I want to find the strain the material exhibits at this force, I have to now look at how does A change. So my A naught is just equal to 2 times R naught divided by square root of 3. But my A at the max will simply be equal to 2 times R max divided by S by square root of 3. So my strain will be A max minus A naught, and then we divide that by A naught. And so that would be my essentially strain value. It's insane. So that is an insane value. I could actually look at the stress of F max, X max divided by A max squared. So it's actually from somewhat reasonable source. But again, this is just a potential, so it's not, you know, it's a kind of made up potential, so don't worry about those values. So let's look at the next problem where we have a polymer now. So I've got a polymer that is described with the Lennard-Jones potential. It has a cross-link density of 10 to the 26 per meter cubed, and I have a TG of 350. So I need to calculate this the Young's modulus at 0, 700, 360, and 700K. So I need to describe my thoughts and any potential problems. So what I need to do is the following. So I need to basically delineate this. So below TG, my material must act like a metal, a solid, etc., etc. So I'm going to use these expressions, and specifically I'm going to use, actually, sorry, when I describe the Young's modulus, I'm going to use this expression, but more generally, I'm going to use this expression here. Not d squared u dr squared evaluated at r equals r naught. You'll see that in just a second. So I am going to use this expression below TG. Above TG, I'm going to use our rubber elasticity. Again, I'm assuming that because I'm given a cross-link density, I got this. My rubber elasticity is just nx kt. So nx, n sub x. So let's go ahead and let's calculate that. So I'm going to clear my kernel, and I'm going to get the following. My ULJ is equal to epsilon times basically my sig divided by r to the squared minus sig divided by r to the sixth, like this. And so now I need to figure out my R naught. So we're given epsilon. Actually, let's go ahead and define it up here. So my epsilon is equal to 0.00019 EV times 0.602 times 10 to the minus 19. So that's going to give me my joules. My sigma equals 3.46 times 10 to the minus 10. And my sig, excuse me. So now I look at here, and then now I can take the derivative of ULJ and then we can go ahead and solve this. So we take the derivative and then set that equal to 0. So we can get to the R naught, solve for R in terms of reals. And let's close it. And we want, again, a realistic R naught. So this is my R naught. So that's my R naught. So with that R naught now I could do my Young's modulus. So Y basically below TG, so BTG is going to be equal to 1 divided by R naught times derivative of ULJ with respect to R to the second this evaluated at slash dot R goes to R naught. And this is my Young's modulus. Now, that's at 0K. At 100K, it's going to be slightly less, but we don't know what that is because we don't know what the shape of the potential is. And then for my Y of 360, it's going to be equal to my NX. So my number of crosslinks per unit area is, unit volume, excuse me, is 10 to the 26th power. And then we have NX times K. So K is equal to 1 times 3 times 10 to the minus 23. And so we have K times our temperature, which is 360. Much lower, makes sense. An elastomer or a rubber elastic material versus polymer 700 will be like this. Larger, but not that much larger. Excellent. What if the crossing density increases by 10 orders of magnitude? What would be your concern? So the first concern is that if I increase my n sub x too much, one of the key assumptions that we had for rubber elasticity was that in our cross-linked rubber, in between our crosslinks here and here, for example, or permanent crosslinks, physical crosslinks, could be chemical or physical, this chain was able to kind of wiggle around and we could behave Gaussian. If I add 10 more crosslinks in here, or 10 orders of magnitude more, this is not going to work. Basically, it's not going to behave Gaussian anymore. So our whole derivation is going to break down, and then that's that. So I would be concerned if this is really valid at that point. It'd probably be more like an elastic material. So that's it. So think about the other variables that you can be asked, and then good luck on this problem. And now let's get on to another rubbery problem, rubber elasticity, in the next video. Thanks. Bye.